All right, I think it's time to get started. So last time we started talking about connected sets, and actually we don't have all that much to say about connected sets. So we're going to move on to the next section, actually the next chapter in the book. Connected is the last concept we're going to talk about in the general theme of topology, meaning things about open sets, closed sets, and related concepts, related things like compact sets and also connected. Anyway, at the end last time we talked about this definition of connectedness. So a disconnected set means you can break it into two parts. You can write, so E is disconnected when E is a union of two separate things. You should think of these as like the two pieces of the set E. And in order for it to actually be disconnected, they have to have this property. That property basically says that A and B don't overlap each other, which is to say they really are two separate pieces. The picture you should have in your mind is something like this. If that's what E looks like, then maybe this one is A, and maybe this one is B. They have to be actually two separate pieces, so we require that they have no intersection between them. A and B, they do not intersect. And furthermore, even if you take the closure of one of them, it still has no intersection with the other one. So this is the definition of disconnected. And then the definition of connected is just the opposite of that. So E is connected when it's not disconnected. This happens sometimes with mathematical definitions. It's easier to define like the opposite of what you want, and then you just define the thing as the opposite of what you just said the opposite was. All right, connected is the opposite of disconnected. So I wanted to do a bunch of examples, and then I had just like one thing to discuss as far as connectedness goes. So we started with some of these examples last time, maybe just to refresh our memory. How about R minus 0? This as a set looks like all real numbers except 0. So it's everything over here and also everything over here, but not that one number in the middle, 0. All right. I want to show this is disconnected. It's disconnected. It really is. In order to demonstrate that, we have to demonstrate the two sets A and B, which are meant to be the two pieces. And I think it's fairly clear when you're looking at the picture what the two pieces should be. They should be like that side and that side, right? So I'm going to choose A. Let A be the left side, which is the interval from minus infinity up to 0, not including 0. And B be the right side, interval 0 to infinity. And then to demonstrate that this counts as showing that it's disconnected, you have to demonstrate that those intersections are indeed the empty set. So then, first of all, I can say what the closures are. Remember, the closure means I throw in all the limit points additionally. So A bar, the closure of A, it includes all those points originally in A, but it also includes that one on the end, which is 0. And B bar is similar, 0 to infinity. And we just verify, we check. What is the intersection? A bar intersect B. This would be minus infinity to 0, closed interval, intersect the open interval, 0 to infinity. And what is that intersection? Are there any numbers that are in both of those two sets? The answer is no, there are not. And so this intersection is empty, which is what we want. And then we also have to check that other one. A intersect B bar, but it's basically the same. This time A is that open interval, intersect this closed interval. And again, this is the empty set. And having demonstrated those, it means that E is disconnected. Is disconnected. All right. I have just two more examples of showing that a set is disconnected. Are there any questions about that one, though? I think I did this one at the very end last time, so I hope we're all up to speed on that. Okay, how about let's show that N is disconnected. To do this, you want to try, if it's a really complicated set, you might want to try and draw a picture or something. Try and think about what the set is, and then think of two separate sets which you can break it into. So N looks like this, just a bunch of points. I mean, on an intuitive level, you should say, yeah, it's disconnected because it's not just like one chunk, which is what connected means, intuitively at least. But you got to think of your two sets. Break it into two sets. Any ideas here? There are, of course, more than one way to do this. But your job, to show it's disconnected, you have to say specifically some particular way to break this up into two sets. Sorry, my pointer is there. What do you think? Any ideas?
A can be 1, 2, 3, and B can be
Okay.
later.
A can be 1, 2, 3. And what about B?
N, where n is greater than or equals to 4.
Okay. You're being fancier than I was just going to say this. A is 1, 2, 3, and B is everything else. Why did you choose that one? The answer is, I don't know. It doesn't really matter. You just have to choose two sets so that together you get everything. So like this is the A in this case. And then the B is everything else. All right. Now we do have to verify this business about the closures and the intersections, whatever. So I'll say then, what is A bar? A is 1, 2, 3. What about A bar? That would be, A bar includes everything from the original A plus any additional limit points. Are there any extra points that you're going to get from A bar? No, because there are no limit points for this set. Those points don't accumulate anywhere. They don't approach any other values. So A bar is just 1, 2, 3. And B bar also. B has no limit points. So when you do B bar, you just get the same thing again. And then we can check those intersections. So A bar intersect B will be 1, 2, 3, intersect 4, 5, 6, etc. And this is empty because none of those numbers are in both sets. And similarly, A intersect B. Actually, it's exactly the same thing, right? Because these closures are the same as the original sets. So N is disconnected. All right? There are many, many ways that you could have split it into two pieces. You could have just said, 1 is A, and then B is everything else. Or you could have gone A is all the evens and B is all the odds. That's like way fancier than is necessary, but you can do it. All right? Any thoughts about that one? Excellent. Here's the more interesting one. This one's a little trickier, I guess. Q. Q is also disconnected. On an intuitive level, you should feel like, Q looks like this. It's got points everywhere, but they don't exist in any continuous intervals, right? Because they would have gaps everywhere. So Q doesn't really come in all in one contiguous chunk, right? It is disconnected. Can we think of some way to split Q into two pieces that have these closures the way we want? Here's one attempt. See how you like this. This is actually not correct, but this is an attempt. I'll write it in red because it's not quite right. What about the same idea behind that R minus the 0 thing? What if I just do this? How about minus infinity up to 0? That's A. And B is, well, I mean just the rationals in here. 0 to infinity. Just the rationals in there. All right. So these intersections, what this means is all negative rationals, and this one means all positive rationals. Right? I'm dividing it into two parts, so like A is those ones and B is these ones. Is that obviously a bad idea? Not such a terrible idea. If you check out the closures, what is the closure of A? Any thoughts? It's all the negative rationals, but then you're also going to add in every point that those approach. What do you think?
It's all the reals.
Yeah, all the reals in that range, you mean this, minus infinity to 0? Yeah, actually one small variation of what I just wrote. Yeah, I see some people giving me the hand signal. Be like this. The closed, yeah, it would also include 0 when the original setup didn't. And then B bar, similarly, is all reals in the closed interval 0 to infinity. And if you check those intersections then, A intersect B bar, this will be empty, right? A is just all the negative rationals, not including 0. B bar is all the positive numbers, yes, including 0. But anyway, there's no overlap between those two sets. And also B or A bar intersect B bar also is empty. I said this was wrong. What's the problem with this? Actually, this seems pretty good. What do you think?
Union A and B, we don't have 0, and that's in the
Yeah, the problem with this is A union B here, A union B is not Q, right? Because A union B misses the number 0. So you don't actually get everything, that's like the most important thing, isn't it? To cover up the whole set. Anyone get an idea, though? There's sort of a variation of this that you can use that will work pretty well.
Del square root 2.
Yeah, how about, instead of all that, don't use 0 as this point where the two sets meet up or almost meet up. Use an irrational. So this is the true answer. Almost everything I say is going to be the same, but A is going to be minus infinity to something like root 2. There's nothing special about root 2. It just has to be some irrational. And then B is going to be root 2 to positive infinity. But intersect Q, I meant, right? Only rationals. But rationals in the range, rationals less than root 2 and rationals greater than root 2, right? Now everything else looks the same, only it really does cover up all the sets. So in particular, A union B, it really is all of Q, right? There is no missing point from Q from this description. And everything else is going to be more or less the same, but I might as well write it. A bar, the closure, is minus infinity to root 2, closed interval. B bar, the closure is root 2, the closed interval, to infinity. And it is true, just like before, A bar intersect B is empty, and A intersect B bar is empty. So it all works out. So you got to be a little cute about choosing the sets A and B in that example. But for a typical example, you'll be able to just kind of draw a picture and decide what the sets should be. All right. Here's one more. How about our favorite set? One of our favorite examples: 1 over n in the natural numbers. Right. This looks like 1. Here's 0, half, third, fourth, and so on, not including that point on the end. Is it connected or not? And if not, can you tell me a choice of two sets that separate it out? This one seems like maybe it's going to be hard, but it's not really. It's not weird enough to be terribly interesting. Yeah.
A can be 1.
Yeah.
B can be.
A could be just this one here, and then B can be everything else. And the fact that you have this weird thing approaching 0 really doesn't matter in this example. A can be 1, B can be everything else. I'll just say 1 over n, such that n in n greater than 1, like that. And everything works out fine. When you look at the closures, the closure of B will include 0, but that doesn't matter. I mean, it still has no intersection with A. So, and I just say, check the intersections as before. Nothing really, nothing fancy happens here. All right, it's a weird looking set, but the weirdness doesn't affect the fact that it's disconnected. All right, any questions about that? Disconnected. So connected, it's a little harder to show that something is connected. You have to show somehow that this kind of breaking up into two pieces is impossible, and that's a little more difficult. But I don't want to get into that too much. We're not really going to spend much time talking about connectedness. But I do want to talk about one theorem, and we're going to prove half of this, which relates this business about connectivity in terms of breaking it up into two pieces, is related to something else that I said last time, which is about points being in between other points. All right? Somebody say something? I heard a noise. All right. Points being in between other points. So here's what the theorem says. It says E is connected. This is something I mentioned last time. If and only if when A and B are in E and C is a real number with A less than C less than B, that is to say C is in between A and B, then C is in E. So it says connected set means one where whenever you have two numbers, A and B like that, every point in between them is also in the set. You should imagine the C is some number in between A and B. Connected means if you have 2 points somewhere in the set, then all the points in between them are also in the set. That's another way of thinking about, the set is like in one big chunk. It includes all the in-between points, in between any 2 points. Another way of saying that is you could say when A and B are in the set, the closed interval A to B is a subset. All right? This is equivalent to what I just wrote. Rather than talk about individual points, it just says if ever 2 points, A and B, are in the set, then all the points in between them, that whole interval, is also in the set. Right? That's another way of saying the same idea. Now, this is an if and only if, and actually one direction of the proof is kind of difficult, and I don't want to get into it. It's in the book, but they also kind of breeze over a few little details. I want to do just the one direction pointing in the forwards direction, because that one you can see pretty nicely on a picture. So I want to do this way around. All right? So I'm going to say, let E be connected. And connected is a weird thing to use. The definition of connected means it is not possible to split it into two pieces with those closures. So I'm just going to say, so you cannot separate E. Can I just say separate E? What I mean by that is you can't make a E equal to A union B such that A closure intersect B is empty and A intersect B closure is empty. All right? This is what we use, and then we have to show, or we have to show that this in-betweenness property holds. So I'm going to say, let A be less than B. Let A and B be in E with some number C in between. And I want to show that C is in E. Right? So the picture you should have in mind is, here's my set, E, I have A over here, B over here, and C in the middle. And A and B are definitely in the set. Maybe I'll put a big old dot right there, sort of to indicate that A and B, they really are part of the set. We have to demonstrate that C also is part of the set. All right? But actually, this picture should sort of remind us of one of the examples that we just did. I'm going to just sort of do a little mini contradiction here. For the sake of a contradiction, if C is not in the set E, then that means on my picture, there's actually where C is like a hole, right? There's no point right there. You can use that hole to make a contradiction with the fact that there is no separation of E. Anybody feel like you know what I'm talking about? If C really is missing there, then we can separate E. Anybody think of two sets? This is very much like the example we just did. Maybe the folks at home. I see there's two folks at home. Thank you for being with us. Everybody can see on this. Or somebody else. How can we separate this into two pieces? Yeah, what do you think? Yeah, Great. Actually, one little thing to modify this.
A and B. Small a and small.
No. So yeah, he said don't go from infinity. Actually, just go from A. Actually, you do need to go. I mean, the fact that A and B are in this set, there could be some more stuff over still to the left of A. So you really do need all of those. Although, when I take the union, you're supposed to get E, right? You need A union B to equal E. But in this case, if these are my sets here, then A union B is basically all real numbers except C, right? We don't quite want that, yeah.
So you gotta make it the closed set for the C?
No, if I make it closed, then I still get, the problem is you're getting too much in the union. A union B now is everything, all real numbers, and you don't want everything. You just want it to be E.
Do we intersect them both with A?
Yeah, intersect with E. This is the same thing we did with the Q example, right? You only want the points from E so that when you take the union, you don't get too much stuff. You just get E, all right? Then A union B is all of E. You miss out on the point C, but I'm assuming for the sake of a contradiction that C is not in there, so you don't miss out on C. All right, but then we can show exactly like in the examples. A bar intersect B. What's that? This is interval minus infinity to C. Intersect E. Now there's extra little intersect E's in here, which is not such a big deal, but it's a bit of a pain. Sorry, I need to make this a closed because I take the closure, right? Intersect, and also I got to take the closure of that part too. This is a little weird, but it all works out fine. And then intersection with B. B is just C to infinity intersect E. Anyway, this is empty. Now there's extra like E's and E closures hanging out in there, but they don't really matter because the intersection of the interval, that first interval, and the other interval is going to be empty. So if you further intersect with E and E bar, it doesn't matter. It's still empty. This is empty. And for the same reason, A intersect B bar, this looks like minus infinity to C, the open interval, intersect E, that's A, and then intersect the closed interval C to infinity, intersect E bar, but this is empty. Again, the E and the extra E and E bar don't affect the intersection because it's already going to be empty because of the interval parts. All right, excellent. This is our contradiction, right? Because we assumed E was connected, but we just demonstrated that you can actually separate it out. So E is disconnected, and that's the contradiction. All right, and this, I believe, is all I wanted to say about connectedness. Any questions about that? We only did half of this theorem. The other half is, like I said, in the book. It's a little more complicated, and I didn't want to get into it. They're kind of sneaky in the book. They did another theorem, which I'm not mentioning at all, and then said, we're not going to prove this. This is going to be one of the homework problems. And then this one, they proved using that other one that they said that they didn't prove. They made it a homework problem. So I don't want to get into all that. All right? Excellent. This is the end of what I want to say about connected sets. And in fact, this is the end of chapter 3. Let's talk about chapter 4. We're not going to get too deep into chapter 4. What I would like to do just today is sort of an introduction to the topic of chapter 4, which is all about functions. I'll put an exclamation. Functions. We haven't said anything about functions yet, which is like usually you talk about functions all the time in mathematics. And in fact, you know, especially since from the beginning of class I said a major theme in this class is going to be talking about limits. You probably thought I meant limits of functions. We've been talking about limits of sequences all along, but we are going to talk about limits of functions also. So for now, for today, I just want to talk about functions in general, and my goal for the next 20 minutes is to describe to you 2 wild examples I like the wild examples. I don't know if you like the weird examples. I kind of do. You know, you got to understand ordinary examples. But oftentimes the weird examples are the ones that really show you sort of what's going on. And of course, we're all very familiar with ordinary examples of functions because that's what you talk about all the time in your mathematical youth. You spend most of your time talking about functions, don't you? And actually, I thought maybe I'd give you a little bit of history here. So before 1800s, mathematicians generally thought about functions, I would say much in the way that kids today think about functions, or even high school students. And it's just not I'm not trying to demean kids and high school students, but I'll say it this way. People thought of functions. If you said, for instance, to somebody like Isaac Newton, what is a function? He wouldn't, I don't know what he would say exactly, but he would not say like we would say, if you ask me what is a function, I would say a function is any kind of rule which associates, if you give me some input x, I tell you what the answer is, like y or f of x. That's how I think of a function, as if it were some kind of an abstract machine where you put something into it, something else comes out of it, right? That's what a function is to me. And this is the way that people in the modern times think about functions. But a long time ago, before the 1800s, people thought of functions as just some sort of collection of known, I'll say, formulas or curves on a graph, right? So if you ask somebody like Isaac Newton or someone around that time period, what is a function? They might respond by just telling you a bunch of examples of functions. They say, well, I know a lot of functions. I know x squared, I know x cubed, I know the square root of x. I know there's a whole sort of collection of things which are functions. And they describe ordinary relationships between things, most of which are motivated by things which exist in nature. So they would have included polynomials, rational functions. That means a fraction involving polynomials on the top and the bottom, right? Rational functions. Getting dings here. Sorry about that. There's also the trig functions, right? They love the trig functions. There's exponential and logarithmic functions, etc. Right? And we study these all the time. And there were even more, like in the old days, they used to talk about all kinds of functions that we don't really talk so much about anymore, or at least we don't learn about them in school. There are things called hyperbolic functions. There are things called, like they have names for things, Bessel functions, stuff like this. They're interesting in physics sometimes. I, as a mathematician, I don't really think about these weird functions all that often, just because I don't do that sort of stuff in my own personal life. But anyway, one thing that you will notice, there's nothing really wrong with this viewpoint, but a function, you don't really get to describe anything you want with a function. There was always some kind of cultural baggage where it doesn't really count as a function unless it is useful for something, or unless you can draw the graph of it or something like that. So I will just point out, these are all continuous and differentiable. That is, you can take the derivative. And you can take the integrals too, right? These are all continuous and differentiable. In fact, it wasn't until the 1800s that anybody even considered the idea which we now have as continuous. They were actually doing derivatives before they even thought about continuous functions, because nobody ever cared about something which was not a continuous function. So these are all continuous and differentiable. And can I just say, this is a little informal, but what's happening? What I'm saying is, people didn't even think about, what about functions which are not continuous? Because they didn't really consider those to be functions. But by the 1800s, late 1800s especially, people started doing all of mathematics in terms of set theory. And it wasn't until then that it became convenient for you to say a function is anything whose domain is a set and whose codomain is a set. And you plug an element in and you get an element as the answer, right? So this is how we now think of functions, but nobody thought to phrase it in that way. But anyway, in the 1800s, people really started to make some crazier examples of functions. Is this going to be backwards or something? No, it's all right. People made some wild examples of functions to try and sort of push the envelope as far as what really counts as a function. And I imagine there was some temporary controversy, although nowadays, basically anything counts as a function. If you can describe how you get the answer, then it's a function. There's no other requirement. So people made wild examples of functions. I want to talk about two such wild examples in our remaining 15 minutes. The first one, they're both pretty wild. The first one is easier to describe. The first one is called Dirichlet. This is the person's name. Dirichlet or Dirichlet. I hear it both ways. Function. It is this. Both of these are just functions from real numbers to real numbers. It is the value, it's one of these weird, like in cases, with two pieces, but the pieces are wild. One, if x is in Q. 0, if x is not in Q. Can you draw a graph of this function? Falling apart. Well, the values are always 0 or 1. But it's hard to draw a graph in the traditional sense, right? For all the rationals of course exist everywhere. The values there are all 1. So up here I'm writing a bunch of values which equal 1 for every rational. You can't really draw that, but because these points should be sort of infinitely packed in there. And then for every irrational, you get 0. So you get another bunch, another sort of cloud of points down here, all right? Because the irrationals also are like infinitely, densely packed. So you get sort of a haze of points here and another haze of points down here, all right? Some interesting properties of this function. Is it continuous, would you say? No, I mean, we haven't given a real definition of continuous in a real sort of technical sense, but you ought to feel like, I hope you feel like, this function, if you like proceed from left to right, what happens is the values just go up and down like crazy, like infinitely often everywhere. So it is not continuous, and in fact, this is likely the only example you've seen, unless you've seen some wild examples before. This function, f, is not, well, I'll say discontinuous at every point, isn't it? In a calculus class, a typical problem would be, I give you a function, I say, find me where are the points where it's continuous and where are the points where it's not continuous. And typical example from calculus would be, maybe a function that looks like this, or something. Here you say it's not continuous at that point, or maybe a function which has an asymptote in it. It's not continuous at this point and also at this point, right? But this is discontinuous everywhere, or it is not continuous anywhere, right? That's really wild compared to other functions that you know of. Typical function from calculus is like continuous everywhere except here, 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 and here, all right? But not so for this one. This is continuous nowhere. Check this out. Simple variation. Maybe I'll save the second the second wild example for next time. But here's a simple variation on this one. I'll write the formula first and then we can try and draw a picture. It's a similar two pieces. I'll call this one G with the Q's, right? But this time, the only difference is this, X. If X is in Q, 0 if X is not in Q. Right? X or 0. It used to say 1 or 0. So when it said 1 or 0, the graph looked like sort of a horizontal line here and a horizontal line here, where these are each kind of a broken up cloud of points. What's the difference this time? Can anyone say what will the graph look like this time? It's different. Not exactly these two horizontal bits. Although I think this one will be the same, right? The thing about 0 is still where it goes. This one is not going to look the same. What do you think?
Like a diagonal line?
Yeah, this part of it looks like y equals x, right? Which is this line this way. Only it's only for the rational values. So here I get sort of I'm drawing it like a line, but really it's a bunch of disconnected points on that. And also on this one here, all right? It's not a huge difference between the previous example, although this one has some interesting properties as far as continuity goes. Is it continuous overall? Certainly not. It has this, if you're sort of moving from left to right, it has this jumpy behavior everywhere, right? Almost everywhere. Actually, at 0, this turns out to be continuous, right? Because the jumpy is not so jumpy right there. They actually kind of meet up, right? You have to think about what really continuous means. One of the folks back home left. He bailed out on me. Sorry, Colin. Can't hear me anymore. Near the origin here, the jumpy doesn't happen anymore, right? Because if you think about what does continuity mean, we don't have a real definition yet, but it means basically if the x value is really close to 0, then the y values are really close to f of 0, which is 0. And that actually is true here, even though this wild behavior. So this one here, G, is continuous at x equals 0 and nowhere else. All right, continuous at only one point and not continuous anywhere else. This is pretty wild. Very hard to come up with an example like that, other than this one. I mean, once you see this one, you can make simple variations of that, but interesting and wild example. All right, I think we have a few minutes left, but I think I'm going to leave it at that just because I don't like this doing the Blackboard thing. All right, sorry about the technical issues. I don't know what my problem is lately, but I'll see if it works now.